And in that case, controlling the totem pole converter by making sure that your THD is smaller, unity power factor close to unity power factor is achieved, and high efficiency over a wide power range. And that those are the challenging requirement. And this digitization is happening much before. I mean, it is much older version. People use digital control for PFC converter. Similarly, LLCs are also been digitized long back, high power, and they use microcontroller, kind of modular application. And this particular design I am showing, which was demonstrated in our course, and it was developed in ST in Noida, which is our collaborator. So here also people use digital control. So there are many converters which are going on with digitization, and more digital control will come. And I'll talk about that based on different power level, you may not do digitization in all aspects. So there will be some limit how much digitization you can do, because if the power requirement is some hundreds of milliwatt and we are working on, they are making digital control will be very difficult because the power requirement is already low. And if you put digital, you require ADC, DAC, then it will be penalized in terms of cost, power requirement. So you have to be careful about the digitization in wide range of application. Whereas if you talk about 5 kilowatt, 3 kilowatt, then you can use microcontroller which may consume few watt, which will be negligible compared to the total power level. Now the question is why and what and how this digital control. So there is a going trend in digital control in commercial product. What level of digitization is suitable for various power level, various market segment? For example, there are some market, if you go to like automotive and all, where the price is of concern, you need to have a very low price. So because the price sensitive area. But there are other applications, if you go to aerospace application, defense application, where the sophistication is the highest priority rather than price. So you need to trade off between the complexity and the digitization based on the market segment. Then what are the implementation platforms? Should it be an ASIC? Should it be a standalone microcontroller? Then what are their hardware, software? These things are always very important. So this require an combination of scientific, engineering, and the technology skill set, and it is the bridging gap between the academics and the industry. So keeping that in mind, actually we developed this course in digital control in switch mode car converter. This course is the first course actually in the NPTEL platform, which correlate between architecture, theory, simulation, and implementation. And it has a lot of hands-on practice, example, synthesized code, and a lot of practical demonstration. In fact, these kits were developed by us, and we should make some of these modified design available for open source. But this kit is off the shelf, and in future that also can be made in a single board. So in this course, actually, we have demonstrated basic feedback feed-forward control, different architecture and modulation technique. If it is a variable frequency control, then what should be the sampling technique? Then what are the level of digitization based on the performance and the cost trade-off? Then this course we also demonstrated various MATLAB custom model. Suppose if you want to implement a digitally controlled converter where you need to specify some timing instant where you want to sample, customize, or if the sampling instance are non-uniform, how to implement in MATLAB? Those things are also demonstrated. Then different modeling, analysis, design tools, then various Verilog programming, very detailed Verilog programming, they are hands-on prototyping. And we also have invited lecture from ST Microelectronics on STM32 microcontroller platform, then also C2000 series for Texas Instrument expert. So this course will actually be very helpful for the skill manpower development, and it will try to bridge the gap between academic and the corporate research. Now coming to the point, what is the primary objective of a DC-DC converter? So it can be any converter, but for the DC-DC converter, we need a very tight voltage or current regulation based on the load. The load can be LED light, then the requirement is different. The load can be processor, the requirement is different. So then if it is a solar application, it is different. So there are various applications and you have to identify what are the requirements. Then high efficiency is of course required for every application, but the first transient requirement are very critical for, let's say, processor power supply, automotive design, and even if you go for EV, for high torque requirement also DC-DC converter has to be fast. They have to be stable, and the power density, that means size, has to be smaller. Now, the primary objective of the converter can be broken into 4 pieces. One is a static objective, which talk about ripple criteria, which will decide your capacitor, inductor size and all. The dynamic objective, the transient response and other bandwidth and all. Then operating requirement, which will talk about hot swapping, which will talk about EMI and other requirement, and then fault protection, short circuit protection, then overcurrent protection. All these are part of objective. So we have to design control which can meet all this together. So in the dynamic and static, the dynamic has transient response. We need to reduce overshoot undershoot so that the capacitor size can be reduced. We need to ensure different kind of stability, which can be fast scale, which can be small signal, large signal. So fast scale means it may lead to subharmonic oscillation. Small signal means we talk about transfer function. Large signal means the system can collapse if you do not properly switch in the phase plane. It can operate into a region where it can be in the rejective region. Then the audio susceptibility. The static part, it can be high efficiency, is very important. EMI is also very concerned. Then power density and line load regulation. But we also need additional requirement. That means the controller has to be reconfigurable, because we do not want to use a fixed gain throughout, because that will be a worst case based design and it cannot meet the present performance requirement. Then the present IC required to cover wide range of current and voltage, and you have to ensure high efficiency over a wide range. So it has to be multi-mode control sort of thing. You have to optimize the dead time for various power level. Then you need to have a coordinated control, because in a network, let's say in your mobile, there are many such converters. So you need to coordinate. For example, because if you go to mobile phone, many mobile manufacturer, suppose if require 4 buck converter, if you use a single buck converter input filter, then it will be bulky. So it cannot afford. So what they do, if you keep, let's say, 2 buck converter common input voltage and using a 1 input capacitor, for example, then you can switch in such a way, you can reduce the input ripple such that overall filter requirement will go down. So that means we want more coordinated control among many converters so that the overall size of the system level can be reduced. It is not just an individual converter point of view. We have to look into the multiple converters together. Then we have to do EMI reduction, safety and reliability. All this require digitization. But coming back to the basic requirement of the converter, I am just showing a buck, but it can be boost or any type of isolated converter. The first thing is that we need to take some feedback signal. So it's a feedback sensing, where in some cases is just a resistive divider followed by your op-amp signal conditioning circuit. Some cases we need isolation. Some cases the current sensing, either high side, low side, and there are variety of kind of sensing method. But ultimately we take this feedback signal for certain objective. So we can do this objective is now met by feedback control. Should we use output feedback? Should we use only single loop feedback or 2 loop feedback control, multi-loop? Should we use state feedback? All these possibilities exist, but this requires the first stage sensing signal. Then the control method. Then we can also implement feed-forward control for the disturbance rejection and so on. But all this feedback control has to be translated into gate signal, which require a modulation technique. So it can be fixed frequency modulation. Then you talk about PWM. We can also talk about constant on-time modulation. Then it is also, that means ultimately it has to be translated into this. So in this context, we have the review paper, which is sort of first one of its kind in the power electronics community, which shows various aspects in the present trend as well as the past trend, how the product are going, why variable frequencies are becoming more popular than fixed frequency. I will not say variable frequency, it is like adaptation in the timing is also there. Then if we talk about overall control method, it can be output feedback based control, which we talk about voltage mode with single loop, current mode with multi-loop. It can be ripple based control. It can be state feedback control, where we can go for linear state feedback. We can go for non-linear control, because majority of the product which are IPs are not disclosed, they are using the non-linear control so that they can really meet very, very fast transient response. Then it can be observer based, not all signal can be sensed. then we have to use different type of modulator. Then the feed forward control, we talk about input voltage feed forward, load current feed forward. We also do droop control, because if you go for adaptive voltage positioning, AVP, where the droop level can easily change within the range, acceptable range of voltage, so that you can cut down the current overshoot as well as the transient time. So these things are already placed and it is in product, commercial product. Then all this control can be categorized either in fixed frequency or variable frequency. So all these things are explained in our NPTEL course, which is the control and tuning method, along with some latest trend of large signal based design. Now, why do we need feedback control? Either we have to regulate the output voltage. We may most majority of the cases we need to achieve very fast load transient requirement. We need also protection circuit. We also need to reduce disturbance rejection. We need to supply rejection, EMI reduction. We need to achieve high efficiency flat curve over a wide current range, whether it is possible or not, whether a fixed frequency is possible, or we need to switch between multiple modulation technique. Then consideration, is it the fast scale or it is the slow scale instability? Am I audible? I don't know whether link is hello.
Audible.
Okay. Then whether it is a fast scale or it is a large signal. Then constraint, if it is a variable frequency, how much variation is acceptable, or we can do adaptation so that we can regulate the switching frequency and take the advantage of the variable frequency technique. So these things are also explained in that course as well. So you'll get a bigger perspective. But in generally, when we design a converter, we need different transfer function. One is the control to output transfer function, which is GVD, where if there is a duty ratio perturbation, how it is affecting output. And these are the poles and zeros of standard buck converter. Then there is another important factor which we often miss or we do not consider, is the output impedance, because this is the one which decides the load transient response. Because your ultimate objective, if you want to meet certain transient response, load transient response, you have to shape the closed loop output impedance accordingly. And by that closed loop output impedance, you can meet the desired response. Then GVG is the audio susceptibility. So what should be the closed loop audio susceptibility? Because open loop audio susceptibility, you can see there's a D term which will directly affect the input and output. So that has to be rejected. And in a buck converter, by input voltage feed forward, you can more or less reject the disturbance, but it may not be completely eliminated in a boost converter. So the summary of control loop design, if we take, first we have to identify what converter topology are we going to select. So it is specific to some application. Then we have to design the power stage. Either you can use the steady state criteria and the available product node. Then the suitable modulation technique, whether is it, I think some noise is coming. Is it from my side? Okay. So modulation technique. So modulation technique will decide for what load range are you talking about? What is the stability? How it is going to affect the efficiency? Then suitable modeling technique. What modeling technique should we use? Should we limit to small signal model? Then we are limiting the performance. Then what are the different type of transfer function? Then what is the suitable control method? Then what is the control loop design step? And finally, we have to do robustness analysis. So these are the basic, aspect that should keep in mind in the design of control loop or the switch mode power converter. In the modulation technique, we have to either choose fixed frequency. For that, either pulse width modulation. Phase shift modulation is not applicable for buck, but if you go to full bridge converter and other converter, phase shift modulation is there. In variable frequency, we can go for pulse frequency modulation, constant on time, constant off time, hysteresis control, then pulse skipping modulation, burst mode control. So there are different type of control, but why so many modulation techniques? Because some of these modulation techniques are popular in their segment, and so many products will come up with different modulation for their distinctive feature, or some of them can also mix between this in order to get or meet certain objective. Now, if we want to compare fixed versus variable frequency, the switching frequency is one of the important factors. So you cannot use variable frequency for a wide range of frequency variation. That may not be acceptable. So we need to do some adaptation that will try to regulate the switching frequency. The other parameter is the ripple parameter, then the transient performance, stability, efficiency. So these things are explained in our course. But what is important, in order to meet the requirement throughout the entire load range, we need to go for multi-mode control. That means in high load or the nominal load, you can go for PWM or you can go to PFM. But these two controllers are structurally different, so it might be more resource intensive, or it can be PWM, PSM, or it can be purely ripple based control. So in this context, we have worked on a constant on time modulation technique, which is the same resource can be used to reconfigure into constant off time, and it is just the change of the counter value and the sampling edges. Otherwise, there is no additional resource are needed, and this can actually improve the transient response, because if you go for step down, so from high load to light load, it switch to constant on time. You can maintain constant on time throughout, or you can switch to constant on to constant off. But all this constant on and off, you need to sense current. So if you want to sense only the low side current, then you can go ahead with constant on time. There is absolutely no problem. And many commercial products, recent products are coming up with constant on time. So in this context, you can actually achieve very fast transient response as well as light load efficiency. So these are there in many commercial products. So that means the multi-mode control is sort of very important, and for that also we need a digital control. So then why there is a growing emphasis on digital control? Because digital control allows us flexibility and portability reconfigurability. So for example, if you are developing a new digital control algorithm, suppose if you write in Verilog HDL program, which is platform independent, you can prototype using FPGA, but the same code can be synthesized using ASIC. It can be with different process technology. So you do not have to change the code. It is just a matter of process that has to be adopted to get ASIC out of that. Similarly, the same design, if you make a design, let's say if you actually change the topology, it is just the matter of changing parameter. So that means just a counter value. So it can be reconfigurable. You can change the control algorithm. So that's why it is applicable to a varying topology, varying process technology. It is more flexible. In fact, you have more digital communication. In fact, majority of the commercial product, when you have more than one DC-DC converter, they are coming up with PM bus communication, because in a mobile phone, let's say you have 10 buck converter which are supplying to 10 different loads. One is ASIC, like a processor load, one may be communication device, buck, it may be boost. But imagine they are all drawing power from a battery. Now, if all 10 applications are running in full phase transient, then the input current requirement will be huge and it can damage the battery or it can collapse. So you need to prioritize which transient you will actually respond and which you can respond little later. So that this requires a communication, and that is through PM bus communication. Similarly, if something goes wrong, fault, how do you ensure that you have a fault tolerant converter or control that will work? So that can also require digital communication. And suppose what's happening, let's say you are talking about data center where many such racks consisting of many converters. Suppose one converter module fail, but you cannot shut down the complete data center. So you have to remove and put another. So this is called hot swapping. That means on the fly, you are removing one and putting another. So the control algorithm has to be such that when you remove, you have to slowly come out of the loop and you can remove. When you put it again, you have to have a slower startup logic before you actually merge it with the other converter which are already running in the full phase. So these things are also possible by digital. Then hardware, software, firmware integration, you can also control third-party interface, because the PM bus is a protocol. Because let's say you are using TI digital controller, and or it can be analog also, or analog device or some other company. So how they will communicate? Let's say if they have ADC, someone is using 8-bit ADC, someone 10-bit ADC. So how this data are interpreted among inside the local controller So there can be confusion. So that means the PM bus ensure that it has to maintain a protocol where the data format should be same. Then you do locally whatever you want, but there should be a handshaking and standardization. So that means you can interface with third party. Then you can have high efficiency, lower component count, advanced control. And based on different level of digitization, if it is a digital PMIC, for example, fully integrated, or you have a converter which only inductor capacitor outside, switch control, everything is IC, then you need a different level of digitization. Another example I have shown where the switches and driver are different process, controller is different, then digital control IC is different. That also is shown. The other will be digital control plug and play, which is a microcontroller for high power application. So there are different level of digitization, and this digital control allow to do rapid prototyping, shorter technology and product development time. But there are challenges. That means the cost. So if you are going for high power, you still can afford little bit of cost or power consumption. But for lower power, these are very, very important, because any ADC DAC extra will be expensive. It will take silicon area and nobody will buy it. So you have to be very careful about the selection. This will lead to the different level of digitization. For example, I'll tell you that housekeeping application. I'll come to this point, the basic digitization, and it can go to mixed signal and full digital. I'll come back shortly. Different type of architecture. Is it a fixed frequency modulation or it is a variable frequency modulation? Is it a uniform sampling, one sample or more sample, or it is event based sampling? Is it like a mixed signal where current analog, voltage digital, or both digital? So that also many architectures are possible. Then power consumption, then modeling, analysis and design tool, because there are a lot of instability that can arise due to discretization which may not exist in analog control. Analog control can be more stable. So this also requires tools to investigate. So it's a mixed domain development. Now step one of digital, suppose I am just talking about a buck converter where the whole loop is analog. It is a voltage mode control. You can see you are taking the feedback voltage, error voltage, but suppose this is converter is supplying a processor sitting inside your mobile phone, and this taking input voltage is battery voltage and is generating, let's say, 1.8 volt or 1 volt for the processor. But now the processor, if you go for processor, digital processor, their dynamic power is the square of the VDD and the propagation delay is inversely proportional to VDD. But if your task is high, then you have to use a higher voltage so that the propagation delay is smaller, because you have to meet the real-time constraint. But if the task intensity is lower, if you unnecessarily operate a higher voltage, your dynamic power loss will be huge. So your battery will run out very fast. So you need to do real-time voltage change, which is called DVS. For that, the converter reference voltage has to change. So this requires a minimum digitization, that means DAC. So processor will say, I need this much voltage, so you generate. Then the DAC will generate the analog reference, and then whole loop is analog. So this is a very fast level of digitization. The next digitization, that means through PM bus communication. That means, let's say there are 10 buck converter running in a subsystem system where each of them local controller is analog, but they will handshake through digitization, because if one converter want to undergo transient, then the central that intelligence will stop all converter to respond immediately, because otherwise battery will collapse. So they will get data and see which one require priority. So their data has to be communicated through PM bus. So this is the second level of digitization. The third level of digitization, that means you need ADC DAC, but since they are not in the loop, it can be slower. So data communication can be slower than the actual switching frequency. So that means you need a very low cost ADC to digitize this process. The next level of digitization is that your voltage loop itself is digital. Now it is a digital voltage loop control. Now the problem will be resource, because your ADC sampling should be at the same frequency of switching frequency or higher. So you need to have there will be power consumption, speed, delay, all this will come into picture. The next level of digital is the current mode control, where you have two loop control in analog. So let's say we make the voltage loop digital. Then current loop analog. So you need also DAC to convert the current difference. So this is one level of digitization, and many commercial also IC use it. Here the advantage is that current fast dynamics is retained in the analog domain, you don't need to digitize, but you need ADC and DAC both. Next level of digitization, both can be digital, but since current require more information to replicate the triangular shape or basically ripple, because voltage ripple can be negligible, so you either have to run the current loop ADC faster, or you take one sample and emulate by RAM. There are many paper and research work. So this is another level of digital. This is, I would say, more towards fully digital. So there are different architecture in the current mode control. So in fixed frequency, it can be peak current mode, valley current mode, average current mode. In variable frequency, constant on time, constant off time, hysteresis control. Here also in constant on time, analogous to valley current mode control. Constant off time, analogous to peak current mode control. Hysteresis can be anything. It can be peak current based, it can be valley current based, it can be average. Then the solution can be fully digital, I have shown, or it can be mixed signal. Or that means we need to understand different control architecture and their associated theory. So if we talk about peak current mode control, digital control, then this fixed frequency, you can see here the digitization is different. That means you can see that we are talking about current loop in analog and voltage loop in digital. So here we are sampling the output voltage, then everything is digital. That means there is an error voltage, then controller, then it generates the voltage current difference. This has to be converted to analog, then analog comparator, then the comparator output again goes into digital domain. They are all date time circuit. So your actual samples are captured much earlier than switching because it requires some conversion time, and this conversion time will decide your speed of the ADC that you require. If you want to reduce this conversion time, then you need to have a high speed ADC. That will also increase your cost and power consumption. That may not be acceptable in various applications. But suppose if you use a lower conversion ADC, then the delay can be as large as 1 cycle. In fact, one application we are using low power where it can be 3 cycle delay. So in that case, we need to use some nonlinear or some other analog digital mix. Otherwise, 3 cycle delay is vast because your transient response will be really penalized. But you need to do some nonlinear technique and taking help of some analog comparator so that you can trade off. But you can also reduce the power consumption with lower ADC. So these things are very emerging. So you can come up with many architecture based on application requirement. But interestingly, the delay of this ADC can have a significant impact on the stability, because even the current mode control, we know for D less than, let's say D equal to 0.2, you can have a stable analog control. But because of the delay, it can lead to instability, which will not be there in analog control. And this delay often lead to what is known as border collision bifurcation, like a non-smooth bifurcation typically, which is a tendency of the sampling delay, which may not be there in analog control, and that bifurcation can lead to DTS saturation, and it will lead to large current ripple and it will be lossy, so it may not be acceptable. The other is the constant off time, which is analogous, where the peak current concept is same. It is the same. Only thing, the earlier case time period is constant, here the off time is constant. The beautiful thing here is that there is no problem with the current loop stability, because in constant off time, if you derive the expression of IL n plus 1 in terms of IL n, you will see it is perfectly stable for any duty ratio. There is no stability problem like current mode control, D greater than 0.5 less than, all these problem will not arise here. But once you do closed loop, then there can be instability because of the sampling delay. That's a different thing. Otherwise, the current loop has no stability problem. But what is the problem? If your uptime is fixed, if your input output voltage varies, then it will lead to switching frequency variation. So what you can do, you can play with adaptation in off time at a very slower rate, so that your loop will not interfere with the control loop. And that can be done just by using counter. You don't need any ADC DAC. That is possible. That's why many commercial products use now this constant on time off time control. But in case of digital, since it is variable frequency, how do you sample? So here we propose that event based sampling. By using that event based sampling, you can stabilize over a wide range of controller gain as well as the input output voltage range. The other is the valley current mode control. Let us take an example. We are talking about an IC which is running at 1 megahertz switching frequency, because now ICs are going at a much higher switching frequency because the process technology has allowed. So you want to reduce the passive side. So even if you take a 1 megahertz switching frequency, the time period is 1 microsecond. Now we are talking about a buck converter which is input is 12 volt, output is 1 volt. Then what is the duty ratio? It is 1 by 12. And then what is the on time? It will be 1 by 12 into 1 microsecond, which will be roughly around 80 nanosecond. So the 80 nanosecond is impossible or impractical to complete the convert, like a comparison of the comparator, turning on, turning off of the switches, the drivers. So all this will become, because you need a very, very high speed comparator, you need a very fast turn on, turn off of the switch, which will increase a lot of cost. So you should not use a peak current mode control for a low duty ratio operation for high frequency, because it cannot be practically realized. But if you do valley current mode control where the off time is pretty large, you can easily take all this action by comparator. But the problem will be in valley current mode, you know, for D less than 0.5, it is unstable. So you need to have a lot of compensating RAM, then it is really a problem. So that's why valley current mode is rarely used in commercial product. But if you go to constant on time, it is actually the valley current mode control, but your on time is fixed. Now, if the on time is 80 nanosecond, you can simply set a counter. That means there is no requirement of comparator, there is no requirement of driver, comparator or this. It is just turning on and off the switch. If the switch allows, it is fine. But you have around 420 nanosecond of time, which is enough to do comparison, everything. But since constant on time has no current loop stability, that's why the recent products are coming, 90% products are coming constant on time for low duty ratio high frequency application. But what are the incomplete aspect? The small signal based design has more problem than analog control because of the delay and resource. Small signal based design is not sufficient because it will limit the bandwidth, which is 1/10 or something. But your switching converter are capable to do more, because we want to use all the Laplace transform and the linear toolbox. That's why we want to simplify the model, but we are compromising the performance. Then small signal is not sufficient. Nonlinear control can take advantage. So that is the emerging trend in power electronics industry. But the question is, what nonlinear control will take? Industry is not ready to go immediately by shifting to high-fi nonlinear control, because they have to be very sure about the silicon area. They have to tell their customer about their functional operation. So they cannot go for very complicated nonlinear control. So what is the best way? In this context, we have done some fundamental work. Why can't we design a PID controller, which was earlier designed by small signal model, but right now we are designing PID controller by large signal model. That means we don't want to apply any averaging. We don't want to apply any linearization. We don't want to apply any Laplace. We want to incorporate the ripple and design a PID controller such that it can tend to get the fast transient response. And this was one of the very fundamental work we did. Then we came up with a tuning formula. That means if it is a current mode control with load feed forward, you can have this analytical gain expression. Then if we also do voltage mode, this is also possible. In fact, we will be coming up with digital voltage mode control tuning, large signal very recently, with all the practical constraint. Next, you can do all this tuning current mode. This you can set a practical controller gain so that the controller will not saturate. But what is the outcome? We have shown in our past work. So left side is a PID controller tuning based on relay-based approach. That is a traditional S domain. Here we are using a large signal control, and you can see we have improved the performance by 6 times without changing the controller. But here we are using current mode with load feed forward. But we also have done for voltage mode where there is no current signal as well as load current, but we still can do the optimal control just using a PID control. It is possible. we can do almost time optimal response, which I have shown, which means your transient response can be improved significantly because you are sleeving up very fast. You can also reduce the undershoot. So as a result, your capacitor size can be reduced. Also, if there are frequent transient, if you take, let's say, 1 second window, and if there are 10 such transient come, the energy efficiency because of this transient event can be reduced. So you can have higher energy efficiency. I'm not talking about the steady state efficiency, because at steady state they are the same controller, efficiency will be same. But because you are saving more number of switching during transient, so you can also save power over the long horizon of time. We also did for boost converter. So for boost converter, in fact, I started boost converter in my PhD, where everybody struggled boost converter with the right up plane 0, because it's a highly sluggish system because of the RH0. So people try to play around the controller design by placing closed loop loop transfer function and all. But if we can go out of this linear approach, and if we can incorporate the switching approach, we have shown just by using a PI controller in current mode, we can achieve our time optimal response without any nonlinear control, just a simple PI control. And we have improved the performance by 9 times. But it also led to some more undershoot in the voltage. So if you put a constant in the voltage and current, you can further improve like 6 times. But you can see that. So what I mean to say, that switching converters are capable to achieve much higher performance, but we only want to make the design simple. That's why we apply Laplace. So I think this has to be changed in order to meet the future requirement. So we did it for constant on-off time, and we got time optimal response just by simple PWM as well as constant on-off time control, which was not there earlier. And we got file patent also in this context. Then we applied this technique for LED driving. For example, this work actually we carried out with Qualcomm, where this was related to mobile display type. Most of the mobile phone, you see there are 2 different type of category. One is the like a backlit LED. Another is the organic LED. Organic LED is a different technique. Backlit LED, in the LED screen of the smartphone, in the 4 different corners, there are 4 LED string, and each string has many LED, 8 LED, and the total voltage requirement is around 25 volt. And for the cost cutting, they simply use a boost converter. Each LED is 25 milliampere current. When you go to the full brightness, then the converter will go to CCM, and the conversion is happening from 3.5 volt to 25 volt, which is enormously high gain duty ratio. And what happens when you restart the mobile? So every product has a diode between the output terminal to the input, such that when you turn off the switching phone, then the output voltage is brought back to the input voltage. That is a forceful thing, so that when you restart the mobile, it has to start again from output voltage to start from input voltage, and again it reaches to the output voltage. So this time takes time, and that is why majority of the mobile phone takes substantial time to ready when you restart the mobile. And that is one of the problem that we saw in Qualcomm. And during the startup also, majority of their product, they face an additional overshoot, and that was putting a stress in their device, and there was a actually problem. Then we came up with which is called constant off time based controller, where the same LED driver, same boost converter, everything same. We are also using peak current based approach only, peak current mode, but this time we are using constant off time. And again, I told the off time can be adjusted with the voltage ratio so that you can regulate the switching frequency. But we have used a PI controller tuning. You can see the proportional controller should be such that it will reach in one switching cycle. That means you see, it is starting from input voltage and it is reaching output voltage in one switching, and that is enormously low. But it also has a very high current. In commercial product, they put a current limit. So if you put a current limit, then you take more switching cycle, but it is still 5 times faster than the commercial LED product, and that we published with Qualcomm in this last epic. So that means our large signal control has without changing the design, without changing anything. We have increased the response by 5 times. So that means your LED will be ready 5 times faster if this technology can be adopted. Next task, we work with another industry where we are talking about multi-phase, and the total current was 120 ampere for 4 phase. That means the load transient was happening almost from 0 to 120 ampere. So then there was a requirement for the Intel processor. The transient response should be settled within 4 to 5 microseconds, and the undershoot should not be below above 20 millivolt or 25 millivolt for a 120 ampere load state, because the voltage was 1.8. It was a very stringent requirement. But there are many commercial products which have not disclosed what nonlinear control they are using. So there are many products that use nonlinear control, but at steady state they use linear control for current balancing and all. What we did, we have extended our large signal control to multi-phase, and we found that we are able to meet and break all the performance that are available in commercial. So we can actually apply our PID tuning for multi-phase, 4 phase, and also all this phase balancing, everything was happening. Similarly, we also worked on DC grid. That means if there are two converters in parallel, they have connected to different type of load, what should be there are a lot of work has been going on for resistive group control, tuning control, but we have extended our large signal control, and we saw that we get fastest response in this kind of application. That means the large signal control can have wide range of application for various products. So summary of the key feature, that means I have told you the digital control can offer small signal tuning, which has been using for many time. Then you can tune the controller in the S domain and get something better in analog, but that cannot export the full potential. You can also do large signal control, which I demonstrated, and you can reach the performance up to the limit. And that is the future trend of the commercial product, because people want fast transient, because they want to make a smaller size, they want to meet a very stringent requirement. Then the controller configuration, that means you need to achieve high efficiency of a wide range load and fast transient. So you need to configure between two controllers, but they should share common resource, and those things are possible in digital. You need to do dead time optimization for high efficiency over a wide range, EMI, and it has to be scalable, and you need also hardware software. So all these support that the future trend of power converter control, digital control has really aged, and it will go a long way, but that requires a lot of innovation. So finally, I want to say that this is the kind of work that we are doing, like computational load for data center application, gallium nitride based power supply for ADAS, multi-phase converter, portable mobile application, automotive application. We are also working on power management IC and some aspect of solar. What is another very the strength in our group is that we came up with a lot of analysis and design tool, including large signal analysis, including large signal control, which are unique, I would say, in order to achieve fast transient, in order to identify a lot of instability where the commercial product was there, what are their drawback, what are the limitation, and how to overcome. With this, I want to finish it here. Thank you. So if you have any question, yeah, thank you very much. So am I audible? Hello? Hello? I don't know whether I lost the link. Yeah. Yes, so am I audible?
Yes, sir.
Yes, sir.
Yes.
Yeah, so I'm done. If you have any question, yes.
Any participants have any questions? Okay. So Thank you, Santanu, for such a wonderful
Yeah, thank you.
presentation. It was really a practical presentation, I can say.
Yeah,
And
thank you.
obviously, participants can, as Sarah said, participants can, if they have any doubt or any other queries, they can follow his 2 lectures also, which is
Yes.
available in the YouTube. So, if there are no questions, then we can conclude this session.
Thank you.
Thank you,
Thank you.
Santanu. Thank you,
Yeah,
Santanu,
thank
once
you.
again.
Yeah, thank you, Shon. Bye.
Bye.
We shall meet again on tomorrow at 9 a.m. for the forenoon session. The session will be addressed by Professor Pravat Kumar Rai sir, NIT Rourkela, and Professor Suman M, IIT VHU. Okay, thank you everyone.